Please help me welcome Abe Collins.
Thanks. Oh, I'm less nervous. We cleared out half the room, it looks like. So everybody recognizes this picture from yesterday, and I was so impressed with the condition of the Judy's cattle on that fescue base. Really impressive what those genetics are achieving. I put this presentation together with the hope of reconciling topsoil formation and livestock gain on grasslands. And I've been finishing cattle for a number of years, but I milked cows before that. And I learned a lot of lessons from dairy that I've tried to drag over with me to beef cattle. So we get a lot of gnawed-off grasslands as we fly and drive and walk around the country. We've got a lot of erosion. It's estimated that 10 times, the soil loss rate is 10 times the soil formation rate in the US, and this is the most advanced industrial nation on Earth, with a long history of battling erosion, soil loss, and the related problems. We've got the flooding, the drought, and the dirty water. If you look at this picture, the green and the yellow are corn and beans. So we have all these eroding acres growing grain for ruminants, and the question comes up, what are the long-term feedlot prospects? I don't think they're high. And then we have this shrinking cow herd. And I think this is in the context of we've used up most of our topsoil. This is the legacy that we have right now, and we can't pass that on to our kids, so we obviously have to reverse it. But we're gonna need a lot more livestock, a lot more livestock. So when I hear about a shrinking cow herd and all this, the question comes up for me, we need to reverse that. This isn't just a matter of economics or people eating more beef. We need tens and maybe hundreds of millions more cattle just in the United States to reverse this decline. So this is the larger context, and this is the story that I tell myself every day, speaking of beliefs. And it's one that I hope that we can get a lot more people on board with. That's a feedlot from space, and some algal-infested pond. This is just one example. This is a small data point. I'm always looking for examples of outliers, and I'm going to ask this room in a minute about what kind of gain people are getting. But here we are, feedlot rate gains in Alabama, Marshall ryegrass. And the Gulf didn't perform so well, not nearly as well, in fact. This was in 1998 and 1999. And 4 different trials, they had an average rate of gain well over 3 pounds for 140 days, 110 days, 100 days. That's a pretty good run. I'm really impressed by that. There are a lot of people achieving a lot more. I've had animals gain for some months at a time at 4 and more pounds per day, but usually those are outliers, and that points to genetics, the value of genetics, and certain animals are just well suited to growing on grass. And I think we all know that, but I'm not going to focus on genetics because I don't want to say the wrong thing in front of everybody I talk to. Their particular genetics are the right ones. This animal pictured, I wouldn't want a herd full of animals looking like that, but there that guy is gaining 5 pounds of gain a day for 112 days. That's astounding. Talking with people, talking with my friend John about production in Tasmania and on highly mineralized soils, the herds are gaining 2.5 kilos a day, about 5 pounds. Amazing. So I think we have this, finishing cattle for me on grasslands is more than just the cheap way to do it or the obvious health benefits to customers that we become accustomed to hearing about. This is really an environmental imperative. We need this herd to grow, to fix the soils in our country, in our communities, on our farms. Finishing cattle on grasslands is a way to rebuild soils, and this finishing cattle on grass for me was a Trojan horse. I am going to talk a lot about the parallels between growing new topsoil and growing cattle. R. Buckminster Fuller has a quote that I picked up from my friend Peter, and that is that you never change things by fighting the existing reality. To change something, you build a model that makes the existing model obsolete. And I think we have that potential here, and I know that there are a lot of people in this room who are achieving some pretty spectacular gains. For a while, we were thinking about even calling this conference something to the effect of the 760 million acre challenge, meaning there's a lot of grasslands in this country, and we should really be thinking about how to improve those grasslands and grow the topsoil underneath them. I think just to round it up and off and make it easier to remember, because there's a lot of detail in that, too much precision, we should probably just call it the billion acre challenge. And that's an achievable goal, so that's something to shoot for. But that's what's before us. We're going to need a lot of cattle. We shouldn't really be growing grain and eroding soil under that production model. And we should have them out on that land fixing that billion acre problem that's really a billion acre opportunity in front of us to achieve water security, food security, a different kind of economics. Thinking about the US, almost 2.3 billion acres. Using USDA numbers, 614 million acres of pasture and range. Between there and 777 million total grazed are some of the estimates. 408 million acres of cropland. The numbers for this year are about 84 million acres of GMO of corn, 93% of which is GMO. About 84 million acres of beans, 94% of which are GMO. About 11 million acres of cotton, about 96% of which are GMO. And the enormous percentage of the two grain crops in there going to cattle feed, I feel like, again, it points to the need for us to really develop this ability to finish cattle on grass. So to restate the question, by attending to the needs of plants and soil organisms, can we achieve increased animal performance, per acre production, continual improvement of soil health, and water security? And I'm fairly certain that the answer is yes. One of the reasons I'm hopeful is I made milk on grass for 7 years with no grain, and that was challenging, but really rewarding. I was about 10 years younger than I am today and had a lot more energy even then. And so moving cattle 10 times a day was just fun for me. And part of what I learned in doing that was there were tricks of the trade. I could engage in the carbon cycle, and I could harness solar energy in some pretty effective ways if I was out there paying a lot of attention to the cattle, to the grass, watching energy levels in the grass. Because without feeding grain, that grain is such an easy energy source. It comes in a truck and you just put it in front of the animals and they eat it, and bam, they make fat. But I was challenged with making fat out of air and water. I needed to recombine carbon, oxygen, and hydrogen atoms ultimately into fat molecules. And we did figure out how to do it, and we did pretty well. I don't think we did as well as others have done, but we made progress and we tracked change over time and learned some things. So getting to finishing livestock, here are some, I'm going to keep it very broad. I'm not going to go into a lot of details. There are going to be a lot of things missing. I think that the collective knowledge of a room like this, there's so much more than I can present in an hour or so. But I think we need to be gaining at least 2 to 3 pounds of gain per day to really truly be fattening livestock and putting a tender, super tender, delicious, fatty product in front of people. We need energy, protein, and mineral density in feed. And often in lush pasture situations, I'm from Vermont, where we really do have very lush pasture most of the time. This is not dry rangeland. And for us, energy is limiting rather than protein. We're very commonly at 25% protein. It's far in excess. We use up a lot of the energy that should be going to fat deposition on that cow into running the kidneys and liver to get rid of the excess ammonia in that animal system. But we need that mineral density too, and obviously the minerals come from the soil that aren't carbon, oxygen, hydrogen, or nitrogen. As much biomass production per acre as possible, I'm for that. I need that both for soil formation and finishing cattle. I need high intake and a reasonable rate of passage. Sometimes on those incredibly lush pastures, we will get manure that looked like green paint, simply too much protein and non-protein nitrogen. Again, and not enough energy and roughage. So it was always kind of a balancing act with that. Good water, clean water, nearby. That helped us to make milk, and it's always helped to make beef, and most research I've shown shows that for the cattle as well. And of course, the low stress aspect. Stressed cattle do not put on weight, and that comes down to our handling, dealing with temperature extremes, whether hot or cold, although hot seems to be harder on livestock, various pests, parasites, and keeping the feed quality fairly regular, even between paddocks. You watch people who turn animals into a new paddock every, say, week or something, and you know that the rumen populations of microbes are changing and crashing and going back up and down again drastically, and that's influencing things. So the first year after I stopped milking cows and finished a load of about 150 cattle for another owner, we got average over May 1st through December 1st, 2.25 pounds daily. That's not bragging rights in a lot of places in the world, but in my neighborhood it was. Nobody had been finishing them that. And I did really well because the owner of the cattle offered me a bonus for any animals that I could finish basically by about 19 months, and he didn't expect to pay out at all, and he paid out big wads of money. It was great. So in the neighborhood that was pretty good, and I think that this points to one of the realities of regional variations in finishing potential. I think because of temperature, because of soil mineral status, in the Northeast we have high rainfall, a long history of it, and we have very leach soils. A lot of our cations are absent, the anions have run, and keeping those soils charged with the minerals that produce very mineral dense forages can be challenging. So here's me on the farm where I was milking cows and finishing beef, and this is an organic buffer, and in that buffer, we weren't allowed to farm, and this is a clay farm, and you can see that the soil is not much to brag about. This was a swamp 200 years ago, beaver dam that had been removed, and the swamp drained, and the farm had grown Timothy hay for export to the Boston market for a long time, and then the topsoil caught fire. There was a sudden oxidation as opposed to the more gradual but no less insidious oxidation that goes on as we've been burning off our organic matter. And the farm burned off, so what was left was the clay subsoil, and that had been farmed for about 100 years since. So here we have about 5 inches of topsoil. Here, about 100 feet away, we've done a number of things with the soil, which I'll get into. And we had a really rapid conversion of blue clay to dark, rich, organic matter filled, aggregated, root filled, oxygen filled, earthworm filled soil, and we achieved about 8 inches one year, which was really inspiring for us and was par for the course for the people who are doing similar things that we were. The process, no doubt, was related to something called melanization, which in mollisols is a dominant soil forming factor, and it's essentially the staining of mineral subsoil with carbon. And that carbon, even though it just looks like darkness to us, down at the microscopic scale is habitat and fuel for microbes, and the glues that hold soil together in those little water stable aggregates that have come up again and again, and which are basically the underlying basis for growing topsoil and achieving livestock performance. So we had 18 inches of soil to work with on these fields, and I'll show you some of the pictures coming up here about how that land performed. The method that we used was keyline soil development, which was essentially successive physical aeration of these heavy clay soils with a subsoiler in a pasture base, and allowing the roots and the microbes to continually grow between the physical loosening events, and ensuring that there was adequate fertility for plant growth, robust plant growth, and humification, because making stable soil organic matter takes minerals other than just carbon. That sequence looks something like you have the compacted ground at the top of the picture, and perhaps sparse community of plants. Maybe it's thick, it doesn't really matter. You physically loosen that soil, and then roots grow down to the bottom. Roots are aerobic organisms, and they need that air. In our clay soils, there simply wasn't any air below about 6 inches. And then you allow the pasture plants to regrow. You fill that whole space with microbes and roots and the eaters of the microbes, and do it again, and you keep creating these climaxes in the soil, and you create a new state in the soil that bumps it up here. It's well understood that subsoiling ground will lead to a carbon flush. You'll get mineralization of nitrogen. You'll get some impressive looking growth for a while. More water will fall into the land, but generally what happens is if you just subsoil pasture land, for example, once, you get an increase in productivity and it'll taper off over 3 to 7 years. But if you keep bumping it, you can create a new state in the soil. And it isn't just dragging steel around on pastures, there's a whole bunch to it. But this was roughly the process that we used. Louis Bromfield is was a famous author and an Ohio resident who took some of the most worn out lands in Ohio, farms, and turned them into some of the best farms in a matter of years. And in a book in a chapter that I like very much, it was called On Building Topsoils 10,000 Times Faster Than Nature. And in it, he defined topsoil formation to the best of knowledge at the time that he wrote this book. And that was that all good topsoil is simply a mixture of the original subsoil with an abundance of decayed and decaying organic material. We know now that mycorrhizal fungi take sugar from a plant and make glomalin, which protects them from the outside soil and is a very effective glue and is stable in the soil for up to 50 years. And that glomalin is not the end product of decay. It's a newly synthesized carbon compound in the soil that really is one of the primary glues. So it isn't just decayed and decaying organic material, but rather it's stable, long-term stable organic matter in the soil that makes new topsoil. A lot of people say, well, I've got sand, I can't actually build soil, and yet I just want to throw this out, and it points to the role of mycorrhizal fungi. And this is pure sand right here, and it was, some grass seed was put in it. It was fertilized with a product called Perfect Blend Fertilizer, which is basically CAFO manure, which has been processed, dried, chopped up, mixed with mycorrhizal fungi at a rate of 1 to 2 tons per acre. There's 1 on some of these pictures and 2 tons. And this is about 2 years later. You can see that mineral sand, plants pumping carbon into the soil, that being turned into organic matter, transforming that sand into something starting to resemble something more like a loam. This is the process of soil formation happening in sand. And here we have mycorrhizal fungi inoculated onto fescue, and you have changes in soil carbon. In fact, after a growing season, in the first graph, you can see that the levels of soil organic matter had almost doubled, which is a tremendous increase in a single season. So this points to the power of mycorrhizal fungi. It also points to the fact that even though fescue is hard to infect with mycorrhizal fungi, it is a mycorrhizal plant. It's just that the endophytes it's an ongoing battle between the endophytes and the mycorrhizal fungi. You can see the difference in the root system, of course, too. So this process of soil formation, one name for it is petagenesis. And here's an example of a rock that I broke in half while doing some fencing work in the mountains of Vermont. And you can see around the outside of that rock that there's a dark layer of a protosoil, and it's covered with moss. And the moss had been secreting for a long time acids and enzymes, and melting that rock and breaking it down, and eventually that will be part of a productive fertile soil on the ground. I used that rock to mount a fence post to, and within it we were working to finish cattle. So we're accelerating petagenesis. That process that took many thousands of years to build 2 inches of protosoil, we're hoping to be achieving that on an annual basis. So in this question of how do we grow new topsoil, sticking to broad principles again, like we were with the finishing livestock, the broad principles that seem to stick for me and the ones that I try to think through when I think about soil formation are that I want 100% covered soil all the time, never bare soil. If I have bare soil, I'll be losing organic matter. My life will be in the soil will be degrading. It'll be an unmoderated microclimate. It'll be too hot, too cold, etc. And in effect, the skin is gone. The impact of raindrops is full on. Erosion happens. It goes on. And I want that 100% of the time, and I want it green as long as possible, because how you get carbon into soil is not necessarily through the residues. It's by pumping carbon in via the roots of living plants and the sugars and amino acids that they weep out into the root zone and feed to microorganisms. So with that big rule and that year-long green corollary aim, there's these 8 essential ingredients. And if we're looking at soil formation, we're trying to achieve it and it's not occurring, it's useful to me to think through this checklist. And the first question I ask is it physically permeable? Or is it so rock hard that there is no air, plants will have very great difficulty in breaking through that concrete-like substance? So soil, I mean, it's obvious that the substrate has to be physically permeable so that roots and microbes can move and do their things within it, and mine it, if you will, for water and nutrients. We need a mineral base. It takes minerals to grow plants. The number of essential minerals to growing plants keeps growing as science gets better. I'm not sure if we'll get up to the full periodic table, but we're getting closer and closer every year. And a lot of those minerals are in soils. There are soils that have critical deficiencies, and in which case, to have our agriculture, we typically import them. And I don't think that there's anything wrong with that. That's one of the trade-offs of adopting agriculture, is how we feed ourselves. But we need those minerals for soil, for plants to grow, and for humus to form. Because as I mentioned, humus is not just carbon. Humus is also phosphorus and sulfur and nitrogen and calcium and potassium and on and on. We need air, and so much of the time this is the limiting factor. Microbes are much like you and I. We can go months sometimes without food. We can go days without water. We can go seconds without air. And if we don't have oxygen in our soil system, then our soil system will shut down and not produce for us, and certainly not be able to produce the root growth, the above ground photosynthetic production to generate the sugars that are eventually resynthesized into the organic matter that forms soils. We need water, not standing, but as films and vapors on those aggregates, in between those aggregates. We need the warmth for the microorganisms to live, but that isn't hot and that isn't cold. This is Goldilocks warmth. And we can moderate that temperature. It isn't just a matter of climate. We can moderate that temperature with how we manage the soil surface. So this is something that's very much manageable by us. And then obviously the most important piece of it all really is the living things on the soil and in the soil. The plants, the microorganisms, algae, bacteria, fungi, protozoa, nematodes, springtails, earthworms, moles, gophers, on and on. Everybody down there, and us on top of it. We're one of the living things on it that's pretty important. And our byproducts, and most of those byproducts fall into that category of glues. The glues to hold together the bits of organic matter and mineral portions of the soil. And the fungal hyphae, which are in effect rebar, to lock together those very small aggregates into larger and larger macro aggregates. The intermittent and patchy disturbance regimes, think about CRP ground, undisturbed largely often, and how healthy those soils have become. There hasn't been carbon sequestration that's been measured that I've seen under CRP ground. It's not happening. The disturbance represented by our livestock and by our agriculture, the different things we do, is actually part of what makes the system work. Litter on the soil surface is critical to maintaining the microclimates and the habitat and food for certain organisms that make soils work. But it isn't the primary way that carbon gets into soil. That's via plant root exudates, sap flowing out of the roots, the trade-off, the carbon economy underground between the microorganisms and the plants. If we go through all of these things and recognize that we're trying to pump carbon into the soil via the root systems, we can increase the rate of aggregation, the pumping of carbon, the humification in the soil. We can grow new topsoil. It's very doable. It's within our power, and most of us are doing it every day, I suspect. Getting started in compacted, lifeless soils is tough. And there needs to be often a jump start, an initial investment of work and power and energy. And there are different ways to do that, and I'm not going to advocate very strongly for one or the other, but I'll be covering some of those in the next few minutes. And ultimately, growing new topsoil is about bringing soils back to life. Through history, and especially the last 100 years, there have been some excellent practitioners who have without backing or necessarily a whole bunch of support, just set themselves to this task of regrowing new topsoil. And some of these, they're people who have really influenced me. They have been mostly men, and I think it's high time that that changed. Friend Sykes was an English lay farmer. Newman Turner was an English lay farmer. He wrote Fertility Farming and Fertility Pastures, amazing books that were based on complex, deep-rooted polycultures of perennial herbs, grasses, legumes that were used to disintegrate the soil and permeate it with vegetable matter. P.A. Yeomans, who invented the keyline system of soil formation and landscape design, and wrote one of his landmark books was Water for Every Farm, and the lessons that he learned at that time I think are as applicable today as then. And Louis Bromfield, who I mentioned. These guys thought in terms of building and growing habitat and food for soil life. And they were farmers. They were thinking about producing food and crops and making viable agricultural businesses, and they achieved that. But they were thinking first, they were first, in a sense, microbe farmers. They were growing food. They were making food, air, space, and water for those organisms. And they favored fungi, and they recognized the critical role of mycorrhizal fungi, although we didn't know about some of the important compounds that mycorrhizal fungi make, glomalin namely, until 1996. They would address notable nutrient deficiencies. If there wasn't enough phosphorus, they would import it, bone meal, basic slag, all kinds of products, you know, whatever was available at the time. But they would trigger the system, recognizing that they had to grow the plants and that humification seemed to take more than just carbon. They tried to use organic materials whenever possible, but they weren't allergic to chemical fertilizers if that's what it took to get the system going. They would address compaction and somehow break plow pans. This is where every single one of these guys was a big fan of the subsoiler. So I will throw that out. They tended to use steel to break the pan so that they could farm deep and get the roots down, because they knew that basically soil formation only occurs in the root zone. They would keep the system aerobic. They would cover the surface always. They would plant diversity, or just encourage it or allow it to happen. They would stretch the growing season in both directions through numerous means: drainage, diverse plantings of cool and warm season plants, microclimate creation, landscape design that buffered wind extremes, wind breaks, things like this all matter. They were all paid close attention to grazing. They returned as much residue, litter from crops as possible to the soil to keep that soil covered. And again, they would address the nutrient deficiencies. A few years ago, I was hired to build a farm in central Vermont, and it was interesting because it was a very worn out piece of ground. It had been hayed for decades. It was all sloping land, and there had been heavy erosion in the past. We brought in a herd right from day one. I was building fence on the fly, perimeter fence and interior fence, and grazing cattle. It was only about 65 cattle, but I needed the nutrient cycling. I felt like that was a critical part of turning this land around. And the beginning of the season was hard. There was buttercup and goldenrod and milkweed and poverty grasses and wire grasses. It was kind of a mess. But we were sending the animals over it. I was clipping extensively, just cutting the weeds, which was 90% things that the cattle wouldn't even eat, and dropping it back down. But for the first 3 months of the season, we had 1.41 pounds of gain per day average. For the next 3 months, after we started getting going with some of our treatments, we brought that up to 2.67 pounds, which for us was a major turnaround. The things that we did were we started grazing. We had nutrient cycling beginning again. We were clipping pastures just to return the residue and create soil cover, habitat for earthworms, and so forth. We put down 4 tons of wood ash rich in calcium and potassium, a little bit of phosphorus. And I did a lot of foliar feeding, small amounts of calcium nitrate, phosphoric acid, hormones in the form of powdered seaweed, fish emulsion, micronutrients like calcium, like copper, zinc, molybdenum, cobalt, and sea crop, a liquid mineral sea product that has a tremendous impact on fungal populations in the soil, on crop yield, and on livestock performance. So we were making these soups of foliars and putting them on. But what we were doing was waking the soil up, and in turn, the livestock gain was going up. So here's this overlap between soil formation and livestock performance. And it was really interesting for me to see. Here's an example, and this is where I hope to turn to some of the lowest hanging fruit that I know of for achieving animal performance, like finishing cattle on grass, and also growing new topsoil. This is a farm in St. Albans, Vermont, where I farmed. Here's some enhanced vegetative index imagery composited over 32 days. You can see the land around us is all brown. Much of it's white. That's standing water. The drainage is so bad. These are corn silage, harvested corn silage fields, basically through the month of October and into November. You can see that there are varying shades of green within the farm, and those varying shades of green represent paddocks that are in stages of full regrowth, having been recently grazed, or in medium regrowth. And this is part of how we plan our grazing, is that we send pastures into winter with varying levels of cover for a number of reasons. What I want to talk about is Llewellyn Mansky's research, and he's at North Dakota State University, and someone I respect a lot for what he's learned about the physiology of cool season plants. He calls it activating the defoliation resistance mechanisms in perennial cool season grass plants. And these rules seem to hold for most plants across the board. Not all of them. There are certain sod-forming grasses that behave differently, like bluegrass, for example. But most cool season perennials behave about this way in terms of reproduction. If we're able in the spring to lightly bite the tips of those plants, taking maybe 20, maybe 30%, but hopefully in the 20 to 30% range, and we go in after 3.5 leaves, so 1, 2, 3.5, and before flowering, there are a couple of effects. One of them is that there's a lot of plant left over, and it has sap in it, and it drops that sap to the root system. And the root system, there that sap's intercepted by mycorrhizal fungi, who take that out along the lengths of the hyphae, and in cooperation with bacteria make phosphatase, which solubilizes bound up phosphorus. And phosphorus is such a hard nutrient, it's so critical. That's the energy storage molecule within cells. That's one of the driving forces of growing new soil, growing fat cattle. So it brings that phosphatase back to the plant. It also brings nitrogen and copper and zinc and other nutrients back to the plant. So this is a good design. There's a lot of plant left over. The sap drops down. It has a lot of sap left to feed that mycorrhizal fungi to make that phosphatase and to boost growth for the rest of the year. If we are able to do that, what Mansky's research found was an increase in the rhizosphere volume, the root ball size, of up to 236%. And there were grad students who took big blocks of dirt and with tweezers removed all of the soil and measured these root volumes. So that's, thank you grad students for that tedium. There's another effect, and that is that there are hormonal effects. When the plant is bit at this stage, one of the results is that the apical dominance, the main reproductive stem, which was going to make a seed head, and that was going to be part of the reproductive strategy of the plant, that was the reproductive strategy of the plant, has been thwarted. So the plant has buds around the base, and it shoots out new tillers, suckers, if you will. That's a good thing, because it's actually the most efficient way for cool season perennial grass plants to reproduce. Seeds are very inefficient. Vegetative reproduction, this tillering, is much more efficient. It's the way that most reproduction goes on in our cool season grasslands. With that increase in tillering and that increase in nutrient availability, there's this 64 to 173% increase in tiller numbers in the second growing season in North Dakota. So specific to there. It happens faster where I'm from because there's more moisture. Over 33% of the plant harvested and the rhizosphere actually shrinks. So the root ball grows smaller. which you think about the pruning off of roots that occurs when you bite off more and more of the above ground portion. When only 25% was taken, they had 140% of leaf replacement, so there's a significant increase in total herbage there. 50% of the leaf removed, only 70% grows back. So the old take half, leave half, we should think hard about it. There is a requirement of 100 pounds in the soil profile to the depth, to the rooting depth for this to occur. So we do need, once again, that available nitrogen. One of the things going on here is that the grass, the old notion, I say old, it's not necessarily that old, but there has been this idea used commonly that we bite the top off a grass plant, energy is mobilized from starch storage in the roots, and that initiates regrowth. And that was sort of the thinking behind grazing grass very severely. You know, let the grass grow up, graze it all off, move on. But it doesn't really work that way most of the time. There are plants that actually are very well adjusted to that. But with cool seasons, in the spring when plants are waking up, they are growing from starch storage in the root system, and they've overwintered on it. They've been living off it all winter, and that is what they're growing from. The rest of the year, most cool season plants are growing from active photosynthesis or energy stored just at the crown, at the very soil surface, up to a few inches from the bottom of the plant. So following Mansky's insights, we can grow more grass by just how we time our spring grazing, and it actually extends back into the fall before. We can do the springtime management for soil health and livestock gain. It's the light graze between 3.5 leaves and boot. And I think it's one of the nicer, cleaner examples of the total overlap between animal performance and soil improvement. With the soil health, as I mentioned, I'm getting increased root exudation, which is being fed to those mycorrhizae who manufacture that glomalin, which is 1/3 of all organic matter. And it's also estimated that 80% in a non-fertilized, not a heavily fertilized system, that 80% of phosphorus going to a plant is coming via mycorrhizae. That is the mechanism for getting phosphate into the plant. For grass performance, this cream grazing, I'm growing much more grass. I'm getting much more vegetative because the new tillers are vegetative, and they will be vegetative all year. Most grass tillers don't go reproductive until year 2 of their life, after which they tend to be done. And then that grass plant grows new tillers, and the plant lives on, but it's always through its children. By allowing for light grazing in the spring, there actually is a lot of rejection of often undesirable grasses, which by the second graze, for me, I have many grazes per season, by the second graze, that stuff is all headed out, very tall, very lignified, woody. And with a trample, or sometimes a clip, but usually a trample, we're able to lay that down on the soil surface, and that's our armor for the rest of the season. So I'm creating my litter for my soil surface, and as it decomposes through the year, that's in effect a nitrogen store. And then finally with the animals, in the spring, in the Northeast, on cool season grasses, we have washy grass. And washy grass does not give you very good animal performance because it's mostly water, and there's a lot of non-protein nitrogen in there. So you have very thin manure, you have too fast a rate of passage, you have too high nitrogen levels, let's just say, it's not all protein, and not enough energy. But the neat thing in the spring with this fast grazing and trying to just harvest the very top of the plants and move around the farm in a pretty fast cycle, if you will. I move the animals a lot in the spring. I really use high density in the spring, which is it seems funny to people because I'm not able to trample grass. I'm not really trying to trample grass. I'm simply moving them a lot. But I'll move them once in the morning, and they will graze for a short time and then lay down. And it's just because they get bored. I just want to give them something to do. I probably don't even have to, but I want to give them something to do for about half an hour, and then they'll lay there until I come back again, let's say 11, 11:30, or even noon, and then I'll start strip grazing. And they cannot resist the opening of new grass. Everybody knows that. You open that fence and they have to go to it, right? And the neat thing is since the sun rose this morning, that plant has been making sugar. So the challenge that I've been having with not enough dry matter in that grass starts to resolve over the course of the day. If you used a refractometer, you'd find that your Brix readings are going to typically go up. There are instances where plants will not go up in bricks over the course of a day. Some people have suggested that that's due to boron deficiencies and the movement of calcium and other nutrients and sugars being inhibited by that boron deficiency. I'm not positive, I'm just passing on something I've heard. So I give them a hit in the morning and then I strip graze through the afternoon. And if I'm getting a third more dry matter in that plant, third more sugar, let's say, well, that's fantastic. And remember, just hours before, that was air and water that just got turned into sugar. So it's an easy way to get better animal performance by strip grazing in the afternoon, in the spring when grass is washy. Simple enough. For us, with making milk, that's when we really learned it, and that's why I was glad I was a dairy farmer before I was a beef farmer. It's called paying my dues, I guess. Because I had to milk them. When I first got the beef cows, I kept trying to milk them, but that didn't work out. But we saw it in the tank. We saw it on the dipstick. That just a matter of days later, after we began this restricting morning grazing and allowing afternoon grazing, there was a low producing herd at that point. It was at 27 pounds per day, and we jumped 5 pounds, which was a tremendous increase just by changing when we moved them. So I want every bite to count. If those animals are going to graze for maybe a maximum of 8 hours, then I can take advantage of the daily cycling of sugar levels in those plants by grazing more in the afternoon. And it trains them to be a herd as well. I don't have to deal with heat stress in the spring usually, so afternoon grazing isn't a problem. It really seems to work out. So here's that pasture that I was showing on the satellite imagery, and this is also the pasture with that deeper soil that I showed in the beginning. And this is fall. I put a lot of work into this soil, and the soil was very healthy, and it's a clay soil, and it still did compact, and it was soaking wet. So this pasture went into winter with heavy cover. There's the pasture from another perspective. This is the fall prior. And then here's the next spring. All of that grass, wasted grass, is covering the ground right now. And as April and May march on, this litter begins to be digested very rapidly by that healthy living soil. I'm losing that litter on a daily basis. May 1st, I want to be out here. I was planning to be here first, but the weather's not cooperating with me. I would never buy a pure clay farm with livestock again. I would always get some mixed ground. This was one of the challenges of this farm. May 4th, it's really booming now. May 8th, I've had to start elsewhere where the ground is better, where I do have better drainage, more slope, etc. So on May 11, the truckloads of animals start coming in. I put them on some land that I'd treated pretty intensively in the past with cover crops, with subsoiling, with compost, with biological inoculants, with seed crop minerals, with any number of other minor nutrients and addressing deficiencies. And it was a very strong field, no matter what we did to it. So again, the 11th, first turnout, you can see that this is obviously well past 3.5 leaves, probably up at 4 and 5. Here's 15 days later, it's waist high, pure vegetative, fully recovered. I can't wait 90 days where I am. This grass is ready to graze. 90 days it'll be up here. But on the 17th, that field that I had sent in with all that cover is now looking like this. It's getting ridiculous, and it hurts me that I'm not grazing it. It just keeps going. Here's grass that we grazed very heavily the fall before, and I'm just trying to point out that what we do the fall before carries through to the next spring. And this is a good example. Heavily grazed the fall before, and that shows up as, let's see, that light green area is ground that had been grazed the fall before, and you can see this just way behind. The 24th, things were out of control. I finally ended up haying it. The lesson from Mansky about achieving animal performance and growing bigger rhizospheres, which are how we grow new topsoil, bigger root balls, and harvesting more solar energy, comes through in this. And we're also able to get better animal performance. It is that's the lowest hanging fruit I know of if you're in a cool season situation. We also started grazing taller, and in the context of New England grazing for the 20 years prior to about 2000, there had been rotational grazing going on, but it had been very short grass, 6-inch down to 1 inch, 8 inch down to 2 inch, over and over and over, and there wasn't much root mass, and litter was wasted grass. So this was a culture that had developed, and it was a matter of needing to challenge that belief, and I just happened to pull the straw, and we did it. So we started talking about grazing tall, and I actively held back from calling it grazing high because people were not that enthused about it at first. And what are you, high? This was the question. But we started grazing taller grass. We're basically going for maximum vegetative stage, but not being afraid of it slipping into boot or some heading, because there's always a diversity of grasses and other plants in the mix, and there's going to be animals that are more and less mature. But we started grazing these plants taller and leaving much, much more residual. In fact, we wanted an active, thick, decomposing mulch. And when we started doing that, a lot of stuff started going right. So when we started talking about grazing tall, it was in the context of a very short grass. Sometimes the grass would go past and everything would be headed out. You know, there'd be various grasses 6 and 8 feet tall, but that wasn't desirable. We weren't finishing cattle on that or making milk. That's in our context. And our grasses don't hold nutrients very well. They get rained on, the nutrients get leached, etc. So maximum vegetative, slipping into boot, it seemed to be what worked for us. And we were leaving a lot of residual, which is as much grazing tall as the plant height that we go into. We are leaving leaves to jumpstart growth. We are getting animal performance that was improved because the animals just wanted that first bite and then they wanted to move on. The energy is always higher in the top of the plant, so we were letting them take that first bite, and we were growing more grass for it and getting more animal performance, which seemed to work out. So again, I would offer this, is that grubbing grass off doesn't give you much beef gain. The plants would recover much faster. We were typically getting the same biomass, but in 2 weeks less, as before when we had been grazing everything right down to the ground. We were getting much more moderate soil temperatures because there's now a mulch layer. The earthworms came back like crazy. The earthworms had been basically not present, and they returned because earthworms need litter. And that was great because when soil passes through an earthworm's digestive system, it's acted upon by microorganisms and their byproducts in the body of the earthworm, and what comes out the back end has much more available, much higher levels of available nutrients like calcium and phosphorus and nitrogen. We're not killing and pruning off roots. Pruning off of roots is one way that carbon gets in the soil, but we are doing much less of it. It happens every year. Plant roots are dying all the time. Root tips are constantly growing. People probably know the take half, leave half number or concept came from research by a guy named Kreider in the 50s. And he looked at the various levels of leaf removed and how much of the roots stopped growing. So if you took off 50%, you only had 2 to 4% root growth stoppage. Stoppage entered my vocabulary after I read his research. And at 60%, though, you had 50% of root growth stop, and you'd have a pretty big death event underground. Your plant would prune itself off and eventually would basically stop growing for weeks on end. But you can see at 40% and 30% and 20%, it showed 0% of the roots dying off. The above ground foliage remaining was able to sustain that root system. So, I think this is just valuable research to look back to, but it does point to leave that root system intact and just keep growing more grass up here, because the easiest way to get carbon into the soil, the best way, is from actively being pumped via the root system from photosynthesis, not the pruned roots. And you're going to be getting better animal performance because you're not forcing them to grub off. You're letting them do exactly what they want, which is take the first bite. We also get a bigger rhizosphere when we have taller plants, when we have more mature plants, and when we're removing less. Here's some grass from a Canadian research project that was kept clipped at different heights, and you can see the tremendous difference in the volume of those root systems. Remember, soil formation only happens really in the root zone, or the extension of the root zone that's created by mycorrhizal fungi. So we get the more developed root systems, we get the bigger rhizosphere volume, and getting big roots growing as quickly as possible is really one of the keys. to both nutrient density in those plants, access to water to keep the plants growing, high animal performance, and increasing soil organic matter. This is wild versus cultivated, domesticated rye. Imagery provided by the Land Institute in Kansas. And just look at the immensity of those root systems. That's what's going on in the prairie. It's really something to think about. The amount of soil formation that occurs in there, the amount of tapping of deep minerals. We test soil 6 inches deep often in agriculture, and these roots are down tens of feet doing their work. That's a good thing. These root exudates, here are some of the names of the various amino acids that are secreted by roots, but it's interesting that every plant has a signature exudate that calls in a very specific set of organisms, and the more plants we have, the more diverse exudates we have, the more biological diversity we have downstairs, the wider the range of the different types of enzymes and acids that enable ongoing chemical reactions and solubilization of soil minerals, which eventually is ending back up in the forage which we're feeding our livestock. These dreadlocks that form around roots are the beginnings and are the creation of soil aggregates. So when someone talks to you about, you can't grow soil fast, ask yourself, how long can we create a soil aggregate? In a sandy soil this spring, a flooded, flood deposited sand, we planted oats, and 4 weeks later, all the oat roots had dreadlocks around them. We had begun the process of aggregation by planting these seeds. Soil formation was underway. So we're managing the grazing to provide above and below ground livestock with finishing grade diets. We're finishing cattle, but we're also working to be pretty much managing the microbial livestock as if they were high performing dairy cattle or yearlings on their way to being fat premium steaks. Oh, that's good. I got an unexpected animation. Going back to our challenge in the northeastern situation, and wherever cool season grasses prevail and there's more rainfall, the energy is limiting, and that's important. We're trying to make sugar. We need more sugar. There are plants that do it well. There are ways of grazing. There are times of day, but these are all. It's really important. How can we get this energy into our forages so that the animals can finish and put down and make the proteins and make the fat that make for a fast-growing finished animal. One thing with too much non-protein nitrogen, for example, this goes into minerals, we need sulfur to make a number of the critical amino acids. If we have inadequate sulfur, we're not going to get complete protein formation or just amino acid in that case. One way or the other, if we end up with too much protein, not enough energy, the microbes in the gut still need energy. So they do something called deaminization, in which they strip nitrogen and off of carbon backbones and get at the energy in the carbon and hydrogen bonds thereunder. But then the system becomes basically filled with ammonia, and the cattle, livestock in general, have to get rid of that ammonia. And the organs that do that are the kidneys and the liver, which have to work tremendously hard to excrete that through urine, through milk urea nitrogen, through their lungs, etc. And what happens is we're running those organs at the expense of putting on weight gain on the animal. With taller grasses, we definitely get effective fiber, which is necessary for the rumen mat and cud chewing. At the top of the plant, we have photosynthesis, more energy. Take your refractometer out there someday and measure the top versus the bottom of the plant. It all just seems to work well. Now the flip side of it is going too far over the curve and grazing 6-foot tall grass and asking the animals to take a lot. We simply haven't been able to make milk or really produce finishing gains on grass like that, where I'm from. I've already covered this, but the afternoon sugar boost is a big deal. If you are somehow able to figure out how to move your animals primarily in the evening, just think about it. The plant makes sugar all day long, and then basically what happens at about sunset is it starts dropping that sugar. And it's not quite this clear cut, but it's dropping that sugar all night long until the tank is empty the next morning, at which point the plant starts making sugar again. So we want to intervene. We would like to harvest the majority of that forage during the high energy parts of the day, and that is in the afternoon or the earlier evening. These are kind of typical of the grazing, of the sward appearance that was giving us decent finishes or good enough milk. These are tumble wheels. We love tumble wheels. A single tree makes your tumble wheel not work anymore, but it reduces our fencing time to usually about 1/20th of what it takes to strip graze, because we just grab one end of a tumble wheel and line and walk, and the whole fence rolls down the field. So that's pretty useful. I highly recommend it. We put pitchforks on the end with a reel on either end, and then put these rolling fence posts in the middle. And then just every time we want to move it, you just pick up the pitchfork, walk, stick it back in the dirt, the cattle have new grass. And it makes tapping into that higher energy grass a lot easier. Because if I had to do that with strip grazing, I would have to go take up a fence, have the other fence already put up, and go set up the other fence, and which is just a bunch of trips across the field. So this is the sort of residual we see. Here's an example of tall chicory. This is wild chicory in our case. This is all wild chicory growing in very poorly drained, low clay soils, doing fine, producing a lot. More examples of dairy, cattle, post-grazing residual. A little bit soft on the manure, but not the end of the world. Every year, night length dictates that plants reproduce and set seed. And no matter how tall that grass is, it will go to seed, some portion of it. That's the nature of the beast. At some point I learned to stop fighting it and embrace it, and I think we started coming out ahead and getting better animal performance and overall system performance. And what we would do is just basically allow the cattle be selective, girls, take whatever you want, and only asking them to take maybe 10, 20% of what was there, so that they kept producing meat or milk, and trample the rest. And this gave us our armor for the summer. It gave us gradual nitrogen release. It gave us a moderated soil surface. It gave us a microclimate favorable to the organisms that we wanted. And it's funny how often they'd walk around bobolink nests too. I'm not sure if it's intentional or not, but they always seem to walk around the bird nest even at high densities. And we would leave a couple of tons of dry matter as litter on the soil surface. And this to us is not wasted grass. This is simply an investment in the maintenance of a high production system. It also encourages fungal activity, and increasing the fungal portion of your soil is one of the ways, it seems, to really increase overall production and increase the nutrient density of your feed, which goes to finishing cattle. All of this does add up to an interesting thing, that you get a cooler soil surface in the summer and you get a warmer soil surface longer into the year, because the decay process that's occurring on the soil surface and in the soil generates heat, and that heat will keep things going longer into the fall. This imagery is probably one of the most well-borrowed, myself included, PowerPoint slides I've ever seen. I think Christine Nichols took it, but it shows the difference in temperature between covered soil and not covered soil. And here we have close to 10 degrees Celsius, which if you go back and read William Albrecht, he came up with this following empirical rule, that for each decrease of 10 degrees Celsius, you typically increase soil organic matter 2 to 3 times. So that's very hard to keep your organic matter in Georgia. You can grow a lot more plants over the course of a year, perhaps, especially if other limiting factors to plant production are addressed. But if moisture is high and temperature is ongoing high, that is going to encourage so much microbial activity that you'll typically have a very hard time holding on to soil organic matter. The thing is, again, that isn't purely climate. We can create the kind of soil conditions by mulching soil, if you will, that give us lowered temperature during the warm times of the year and will give us more retention of soil organic matter. So that's a microclimate that we can create. And here are examples of soils that a couple of years earlier had been cracked in the heat, no earthworms, no earthworm castings visible, a very different soil surface. But once we started covering it with all this mulch early in the year and then allowing the soil to digest it, we started getting aggregation. And I don't know if you can see it, it's there. But they're a little, everything's crummy and small, and a kind of point of pride for me became that there wasn't a square inch on that farm that I could find that didn't have an earthworm casting on it. It was just the whole surface of the farm became bubbly with earthworm castings. We started getting aerial roots and so forth. And here you see the little green shoots popping up. These are tillers that were generated in the fall. And this goes back to the Mansky research, that this is one of the primary reproductive mechanisms in cool season plants. In the fall, they generate tillers as well. And if we damage those tillers, that was going to be next year's vegetative growth. I mean, that's a big deal. So one more way to grow more grass, get bigger root systems, harvest more sunlight, have a denser, thicker sward, which all adds up to having every bite that that animal takes that we're trying to finish be a full bite. Because thin swards, the animal simply has to open and close its mouth more, and it's a lot of work to graze and open and close your mouth. So this is part of getting a bigger root system, getting more dry matter per bite, getting better animal performance. Here are animals flattening, late May, headed out grass. Greg's cattle yesterday, when we were out there, when my group was out there on Greg's farm, the cattle were grazing right in amongst us. Those are the most docile cattle I've ever, it was unbelievable. I think he bottle feeds them all. Midsummer, I'm not too worried about density. I'm slowing down a little bit. The cattles are all, pastures are all lush, delicious. The cows just kind of wander around. I like the low stress of this time for them and me. Fall, same thing. Everything's fairly uniform. I'm still grazing knee-high forages, you know, in that neighborhood, sometimes taller, sometimes a little shorter. But we had our first drought, and this is where I really started to appreciate a plant called chicory. And during that drought, which was the summer of 2011, which for us was June 16th to August 27th, when Irene came and kicked our butts. Irene flooded our state big time. And this is why we need more soil that's why we need to be finishing cattle on grasslands to create soil aggregates to infiltrate every raindrop so that we have decreased flooding. But during that approximately 10-week drought, the plants that made it were the deep-rooted ones. Chicory was the outstanding one by far. And chicory, orchard grass, burdock where it was growing, plantain, alfalfa, these are the plants that kept growing. And I realized, wow, these are the really mineral-rich ones too. You know, the calcium in alfalfa, for example. Chicory is through the roof for mineral levels. And anytime I've ever had the chance to see an actual chicory root going down into the soil, they just keep going. Everybody else is kind of doing their thing up in the typical soil profile, and then the chicory root just keeps going. I've started planting pastures with the majority of the plants being herbs, chicory and plantain, numerous types of chicory. And the productivity is amazing, and the forage quality is amazing. In fact, I've determined that grass is third place. It goes forbs, legumes, and grass last. That's what I'm playing with these days. I'm not sure I'm right, but it's a fun experiment, and the cattle are doing well on it. This chicory root that you can see the cross-section of, that's a 1-year-old plant, and that root is about 2.5, 3 inches across. And you can see my friend Chuck with the broken off top of the root, but the thing is the taproot keeps going below it. I started getting back mineral analysis on chicory, and the phosphorus, magnesium, potassium, iron, zinc, copper, and manganese levels have been extremely high, and that all goes to animal performance. So there are some plants that are very good at harvesting, partly because of their physical root structure. Their roots are going way down deep, but also because of the enzymes and the acids that are coming out of them and the microbes that associate with them and the acids and the enzymes that they make. And one of the challenges for me has always been a mentor and a dear friend of mine, Jerry Brunetti, has long advocated for very high mineral levels in forages, saying these are the optimum levels that you want to achieve. It's hard to achieve them. In fact, I was beginning to suspect that he'd set them impossibly high so that I'd just strive for the rest of my life and never reach it. But that wasn't the case. I just hadn't gotten there yet. And now that I'm just starting to play with other plants and fertility regimes, etc., and ways of managing land, and I'm seeing, wow, we are getting close to these very high levels of calcium, phosphorus, magnesium, all these critical nutrients that make up plants' bodies and all the plant, sugars and proteins and plant secondary metabolites that give us our health, that are our medicines, and that are the plant's medicines and defensive mechanisms, and that are the medicines for the livestock as well. And these include hormones. So it goes on, but we need these nutrients if we're going to get the animal performance. I'm finally beginning to see them, and chicory is my plant. My friend Peter tells a story about, I think a government panel decides that it's very important that we all eat vegetables, so we should get together in committees and talk about it. And one guy always shows up at the meeting and he's like, tomato, 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 tomato. And he kind of becomes annoying to everybody, but it's become that way with me and chicory. So I do recommend you experiment with it. Recognize there are a lot of cultivars out there and that you'll want to pick the ones most suitable to wherever it is that you are. Chicory is, has other effects too because it's so deep-rooted. And one of those is that some research in the Northeast showed that over 1/3 roughly of the pasture mix, and that plant taps deep water during dry times and shares it via mycorrhizae with the other plants. And you can get through droughts without a slowdown in growth. So if we think diversity and think underground, we can achieve increased plant growth through dry times by thinking of this really multi-layered underground level. The case study that was done in Burleigh County that showed 7 species cover crop versus monoculture and getting almost 3 times the production, if I'm not mistaken, is one more testament to the power of diversity. And when we go to diversity in soil organic matter, just the simple act of having diversity in our pasture seems to grow more soil organic matter. A Czech study showed that with a 33 species versus 16 species pasture mix, that they had a difference of 59 tons of carbon versus 106 tons of carbon. The species diversity is what seemed to make the difference. So this is sort of like finishing cattle and growing topsoil for dummies like us, humans, when the complexity can be overwhelming. But diversity is one of the rules for sure. And this is one of the books to me that connects the dots in a lot of wonderful ways. And I brought it because I was coming to Missouri, where Albrecht was from. William A. Albrecht was the world famous soil scientist. And he's a wonderful resource for us all. And his book, Soil Fertility and Animal Health, which Charles Walters put together from his papers, really has a lot of the linkages between the mineral profiles in the soil, the nutritional content, the growth characteristics of the plants, the health of our livestock, and ultimately the health of us, because we need all these minerals and all the compounds that are manufactured by the plants and the animals in turn. He points out that having diverse mixtures of plants is critical because the cow is, quote, a capable chemist. And, quote, the cow is a capable connoisseur of the vegetation as it satisfies her physiological requirements for growth, protection against disease, and reproduction. She seems to balance her diet well if mixed herbage permits. So mixed herbage, cocktail cover crops, diverse, deep-rooted pasture mixes. I'll bring this up because soil, organic matter, deep-rootedness, getting a lot of crop per drop when water really is a challenge that so many of us are facing. Ulrich wrote a famous short paper called The Drought Myth, and the absence of water is not the problem. And in it, they had fertilized and unfertilized corn. And what happened was, as things dried out and the plant roots started marching downward looking for water, they ran into real mineral scarcity. The thing is, that's part of the miracle of plant growth, is that plants use very dilute solutions of minerals dissolved in water, pulled up through themselves to manufacture the proteins and all the other compounds of life other than the sugars that get turned into the backbones for most everything else. In the fertilized soil, these yields are so striking. It was 1953, but they got 79 bushels for about the equivalent of 5,600 gallons of water per bushel. In the unfertilized soil, they got 18 bushels, and it took 26,000 gallons, almost 5 times as much, to grow a bushel of corn. Nutrient scarcity in our soil, it's hard on livestock growing, but it's also very inefficient when it comes to water use. So we got to think about that. And this does not just mean, though, that we need to pour on more soluble salt fertilizers. That's one way to do it sometimes. But it isn't always the only way. I have another slide coming up, and I'll point to instances where the simple act of putting carbon into soil and creating the food and habitat for microorganisms can make formerly unavailable minerals available. So I want to reiterate what everybody has been saying about water-stable soil aggregates. This is the key. This is the infrastructure for our society. This is the infrastructure for our grass-based feedlots. These are the things that we have to grow if we're going to grow and finish cattle and sheep and other livestock on grasslands. And it's also the key to water security, flood control, fire control, control of dust storms, erosion control, maintenance of our physical built human infrastructure. But aggregate construction can happen very fast, but it's a continual investment. That's sort of our job as land managers and as the interface between society and the land, is to keep the soil covered and grow these aggregates. It's funny, these are all different ways, expressions or words saying the same thing. Water-stable soil aggregates, tilth, crumb structure, pore space, air and water movement, infiltration of rainfall, water holding capacity, friability. That's like, you know, people who live way up north have 100 words for snow. It's good that we have 100 words for crumb structure and aggregates in the soil because it is that important. Hans Jenny was the father of modern soil science in a lot of ways. And he was real interested in figuring out a formula for figuring out how fast we could grow soil. And he came up with the soil properties basically equals climate, organisms, relief, which is topography, parent material, time, and an open space in the ellipsis. And that open space is there in case we discover some other things. The problem with trying to be so predictive about this, and some of Hans Jenny's ideas, they've slowed us down because there is a notion that soil can only be formed very slowly at geological rates, and that once lost, soil is lost forever. There are still sustainable agricultural leaders who tell us this today, that soil once gone is gone forever. If that's true, we're in trouble, but it isn't, so we're not. There's hope, there's potential, and we need to be harnessing those finishing cattle to grow that topsoil. I think it can be pretty basic thinking through how do I finish my cattle faster or better. Let's not just say faster, but let's say better. How do I grow soil? We can get down to basics. Soil chemical properties, biological properties, physical properties. When we look at our animals, we can think through checklists too. Is the animal stressed? Is there adequate energy? Are there complete proteins? How are the genetics? What is the quality of the water? Are we using every bell and whistle that we can get our hands on? People are using cider vinegar. A sea mineral that I'm a big fan of called sea crop, fed at a teaspoon per 540 pounds, increases rate of gain 8%. That's pennies per day for an 8% rate of increase. Amazing. So thinking through checklists for soil formation and livestock performance, I think is useful. It serves me. What are the limiting factors in either case? We want a lot of photosynthesis. We want a lot of humification. We want oxidation. Oxidizing organic matter is what makes plants grow and what makes the soil system work. It's the discharge of the energy that was stored up in that organic matter that's driving the plant growth machine, the factory, if you will. Respiration, oxidation. But we still want to keep some of the carbon that got fixed originally by the plants and sugars, and we want that to be resynthesized into humus. And that is essentially soil formation. That humus, that glued together, that glue material and habitat that's holding together the soil particles. So looking at some important soil properties that basically need to be lined up, thank you. Surface cover, we need the covered soil. We need aggregated soil, so we need to be thinking about growing the aggregates. We need soil carbon. How are our soil carbon levels? These are all things that can be monitored and really should be as managers, as participants in our communities, as people who need and want to learn faster. What are our available soil mineral levels? Are we being held back by unavailable minerals? How deep is our topsoil? How deep is our rooting system is the same question. Could we deepen our root systems? You guys have dug a hole down and followed a root channel and seen that the soil, the mineral subsoil is darker around the root channel where there's organic matter now. How dense is our soil? Is it compacted? How much biodiversity on it or in it? And we can intervene in all of these points, and it's going to be just a matter of strategy to decide which is the next weak link in this chain of production. But it's interesting, if, for example, intervening in the soil cover factor, we can have 100% infiltration with 100% cover if some other things are lined up. In this one particular study, they had 100% infiltration when the soil was fully covered, but with bare soil, they were losing 3/4 of the water. How inefficient is that? Because we need that water. We need that water to grow those plants, to finish those livestock. Thinking about how carbon gets into the soil, there's residue, yes, we know it's important, microclimates. There's root exudates, those seem to be the key. That is the liquid carbon pathway. There's the sloughed root matter, which as root tips are growing into the soil, they're continually wearing off their tips and tissue on the outside. There's the pruned and dead roots that we've talked about. There's microbial photosynthesis. Algae and photosynthesizing bacteria actually harvest sunlight and make biomass. And then there's hauling in carbon from offsite, which happens sometimes, but not really on a ranching and farming scale too much. Getting carbon from the air to the plant is turning CO2 and water into sugar. Getting carbon into the soil is turning that sugar into more complicated, more complex, longer chain molecules and mixing it with minerals from the soil and also with nitrogen, which originally came from the air, and getting that eventually down into the system via all those methods we talked about, but always the importance of the liquid method. Pointing to the actual needs of minerals for humification, of course the cattle need minerals to finish, and of course the soil, the humus, we need it. So here's a rough ratio, is that if you have 1,000 units of carbon, then you're probably going to need about 100 units of nitrogen, and you're going to need about 10 units of phosphorus and about 10 units of sulfur. So a lot of people put a lot of residue down. This is when we're thinking mostly about residue. A lot of people put a lot of crop residue and they're like, my soil organic matter isn't increasing and I keep dumping all this litter on the surface. If that's the primary way that you were hoping to get carbon into the soil, that is a good time to think about. You can do a simple forage analysis and say, how much phosphorus, nitrogen, and sulfur is actually in that plant relative to the carbon, and are you going to actually get humification from that? So that is a factor. I mean, a lot of that can come from the soil, but it isn't always necessarily there. Going to the fact that this is a great quote from Sir John Laws, it's the physical condition of the soil, its permeability to roots, its power of absorbing and radiating heat, its power of absorbing and retaining moisture that is of more importance than its, strictly speaking, chemical composition. And below it, there's a table showing the levels of nutrients that are often available in sandy loam, silt loam, clay loam. The thousands of pounds of available minerals, but they're not plant available. They're bound up. We need to generate the acids and the enzymes if we're going to tap into them. And that's where this liquid carbon pathway thing comes in really to fore. Here's some data and pictures from Winona in Australia, where Colin Seiss has been doing pasture cropping and is now doing diverse pasture cropping. And by focusing on this mycorrhizal pathway to humification, without fertilizers, they saw increases in available minerals of 277% in calcium, 138% in magnesium, 146% in potassium, 157% in sulfur, and on and on. So that is an option. We don't always, to humify things, we don't have to buy bagged fertilizer. But if we're not going to, then we better be thinking about how we're going to be pumping carbon into the soil, creating food and habitat for the microbes. This is aggregated soil with the glomalin removed, resulting in completely powdery soil. This is what happens when we destroy the mycorrhizal fungi and the glomalin that serves as glue. Here's a good example of some research coming out of New Mexico State University showing that the fungal ratios in soil fungal to bacterial ratios have very close correlation with total production. And so it gives us one more reason to think a lot about growing fungi. I'm getting close to the end, and I hope I've talked about a few things that'll be useful to you in terms of growing more cattle. But I really was basically using the finishing cattle thing as a Trojan horse to talk about soil formation. One trick that came up from Cornell, a guy named Tom Kilser, who I've really enjoyed spending time with over the years, was wondering why the forage quality was so high on fresh pasture versus the hay that he was making. And he realized, and baleage and haylage and so forth, and he realized we drop hay and that plant is still living and it respires a lot of the carbohydrates in it. And we end up with a much lower in energy feed than we have out in that pasture standing there. There is the dehydration, but we lose a lot of dry matter, lose a lot of sugar just through respiration. So he started advocating for hay in a day. And there are times when hay in a day works great and there's times when it doesn't, but the basic idea is to drop hay as early as you drop what will become haylage or baleage. As early as you can in the morning, wide swath it at about 80% of your cutter bar width or more, 85% more is ideal. And then basically let it dry down and bale it and wrap it by that night. And the outcome of that is just a small intervention, but it's 300 pounds more milk per ton of feed, which is, again, it's sort of like grazing in the afternoon. Getting that grass to dry as quickly as possible and stop respiring so you can conserve that energy. Before I get to the last slide, I want to just ask, can anyone who's ever achieved over 2 pounds a gain a day on any sustained basis raise your hand? 1? Oh, okay. Well, the kid from Vermont does have something to teach then. No, I know you've done it, Bob. So some of you have. There are people here who have achieved over 3 pounds a gain a day, I think. Let's say for an average over your growing season. Have you achieved 2 or 3? Close. Well, that's great. I think we can do it. I mean, hey, in the 90s, on conventional herds with set stocking on Marshall ryegrass, they were achieving 3+. So with set stocking, I think, you know, relative to the sophistication of the grazers here, I know that we can start doing this. And I would love to share information with anybody who wants to do this, because I do think this is really one of the more important livestock production challenges in front of us. Figure out how to grow cattle on grass, finish cattle on grass, so that we can stop using land to grow grain and start using our herds to both produce perfect food and fix soils. I would conclude that the same conditions needed to finish livestock are the very same conditions we need to grow new topsoil. It's an absolute priority to grow grass-finished livestock and to grow the topsoil. And to learn faster, we're going to need to monitor our livestock gains, our soil health, rates of infiltration, and how soil and water are interacting, and find the patterns of management that are consistently getting results so that we can all learn from each other. I would like to learn with you guys moving forward over the next 2 years, 5 years, 10 years. And I'm going to encourage you to keep up with both the Soil Carbon Coalition, within which Peter Donovan, myself, and others are all working on tools that we hope will help us to all work together and share data better. And of course, the Grassfed Exchange, where I really had the privilege of working with one of the best groups of people I've ever worked with, who are committed to this industry and to the land and the soil and the families who make up the ranches that are represented here. So thanks for your time.